So we're going to work on the practice problems for unit part 9, part 1. And these questions are going to cover the following. Oh, let me put you guys over here. It's going to work on the following learning objectives: describing the behavior of acids and bases, identifying substances as strong or weak bases, predicting the direction of proton transfer, writing acid and base constants and using them as a predictor of the strength, and identifying water as an acid or base in hydrolysis reactions. All right, so before we get started, let's work on a challenge question. I'm gonna give y'all about 2 minutes for this one. All right, so we're gonna come back to this question later. And we're gonna move on into our next set of questions. So identifying the behavior of acids and bases in solution and identifying conjugate acid-base pairs. So remember, an acid is something that's going to donate a proton, whereas a base is something that's going to accept a proton. And if we're talking about water, water is always, if we're just looking at an acid in water or a base in water, water is going to play either the acid or a base role. It depends on what is in solution with. So hope that answers your question, Sharona. So if there's an acid in solution, then the water will act as a base. If it's just a base in solution, water will act as an acid. All right, so let's identify the characteristics of each of these. Which one has a sour taste? Is it an acid or a base? Good, an acid. It produces hydroxide ions in solution. What do we got?
Base.
A base. It has a chalky taste. Which one is that? Yep, that's a base. And is an electrolyte?
Base.
Acid.
Both?
Yeah, both. Acid and base. And it produces hydronium ions or protons in solution.
Acid.
Acid.
Acid. Good job. All right, so for each of these equations, let's identify the acid and the base in the reactants. For A, which one of these is the acid? So we've got nitrate, or if I give you the name, I'm not going to give you the name. Which one's the acid? Yes, the HNO3 is the acid. And what is water acting as in this situation?
Base.
Water is acting as a base. You see that, Sharona? Notice
Yes.
that. So tell me, is this a strong acid or a base looking at the equation? I mean, is HNO3 a strong acid looking at the equation?
Yes,
Yes,
strong.
it is. Why?
The arrow.
Yep, one arrow going forward. And if it's a strong, no, I won't ask that question. All right, let's look at B. HF plus water, which one is acting as the acid?
HF.
And water is acting as the
Base.
base. So there are specific acids that for this class that we're going to classify as strong, and everything else is weak. And we'll get to that in a minute. All right, now we have an acid-base reaction where we have an acid plus a base. Which one is acting as the acid? HNO3. And which one is the base?
NH3.
Yep. How do we know, though? Even if you didn't know which one was the acid or base, how would you know which one was the acid?
The one that donates the H.
Yep, the one that donates the H. And how do you tell? How can you tell who has donated the H? Okay, so you see one extra hydrogen on the nitrogen, on the ammonia becomes ammonium, and then we end up with the NO3 minus. So you have to look at your products to determine what has happened. So does this equation represent a strong acid or a weak base?
Weak because it has 2 arrows.
No. Nope, this is completely different. This is an acid-base reaction, period. where we have an acid plus a base. So this is just showing that acid-base reactions make it to an equilibrium situation. If I just have an acid plus water and I've got double arrows, then that lets me know that I have a weak acid, right? Whereas if I have an acid plus water and I have one arrow, that shows me I have a strong acid. But this is just showing this is an acid-base reaction, and it's just showing me that equilibrium can occur with these two reacting together. All right, let's take a look at the bottom examples. Which identify each of the following as a Bronsted-Lowry acid or a base? A, PO4 3-.
A base.
It's a base. Why?
Because it is the one accepting hydrogen.
Yep, it doesn't have any, it has a negative charge, so it can accept hydrogen ions. So what about HClO4?
Acid.
Yep, it's an acid. And what about Cn-?
Base.
It's a base, right? It has no hydrogens to give. It can accept those protons, so it's a base. So what does this show us? That polyatomic ions always act as a base if they're negatively charged. Got it? All right, next question. Let's look at the answer to this question. The answer is B. Oh wait, the answer cannot be A because iron 3+, that's a positive, that's a cation. Doesn't have a hydrogen to donate. And it's a positively charged metal cation. Cannot be an acid. Acids have to have hydrogens. C is ammonia. Memorize this. Memorize. Ammonia is always what? A weak base. Remember that. And nitrate is a what? It's a negative polyatomic ion. So what does that say? It's a negative polyatomic ion, so it's actually a base, not an acid. All right, next question. All right, so what is the answer to our question? Well, D is the answer because it is the only one that can accept a hydrogen or a proton. Oh, A is a what? What's A? A is an acid. What's B?
Base.
No, it's
No,
not a
no.
base. No, B is the conjugate acid of ammonia. Correct, John Hansel. Perfect. And the nickel 2+ ion is just like that iron 3 ion. So, what you call it? There we go. It's a cation, so it cannot act as a base. All right, let's do some conjugate acid-base pair practice. So let us determine whether who is the acid and its conjugate base, and who is the base and its conjugate acid. Now we know that when an acid loses its proton, it becomes a base. When a base accepts a proton, it becomes an acid. So who is the acid in this reaction? This is actually a repeat of the previous question we had on the practice page, but to the next level. So which one? All right, so we get HNO3 is our acid, and Simone, yes, the base, the conjugate base is, I thought I had it in a different order. All right, so the base is going to be ammonia, and the conjugate base for the acid is the NO3-, and the conjugate acid is going to be the NH4+, right? What's the difference between them? is the difference between them is 1 hydrogen difference, right? Notice that here the HNO3 has 1 hydrogen, the NO3 has no hydrogen. Notice that the NH3 has 3 hydrogens and the NH4 plus has 4 hydrogens. So that is how we determine. All right, write the conjugate base for each of the following acids. What would be the conjugate base for A? Like Br minus. What would be the conjugate base for H2S? Yes, HS minus, because remember, this is a neutral compound. When we lose one of the positive charges, then it becomes a negative charge. So you guys are almost right for C, almost. Yeah, you got to have that negative charge in there. So whenever you lose a proton and it's a neutral substance, you end up having a negative charge. All right, let's write the conjugate acid for each of these following bases. What's the conjugate acid for HNO? I just gave y'all the answer. HNO2. Nope, not plus, Veronica. It's not a plus sign because I have a -1 charge and then I just add a proton. So it makes it neutral. So B, yes, we're going to have NH4 plus, because this is neutral. I add a proton and it becomes positive. And for the last one, what do we have? Correct. Water, H2O. Okay. So which one of these sets contain conjugate acid base pairs? You list them out in your answer. Give me all of the ones that have a conjugate acid base pair. So let's check it out. Number 1 is a conjugate acid base pair because there's only 1 hydrogen difference. Number 2 is not because it has a 2 hydrogen difference. The conjugate acid of CO3 2 minus will be HCl3 minus. Number 3 does not because our negative ion is completely different. So the conjugate acid for HClO4 minus would be, for ClO4 minus would be HClO4. 4 is a conjugate acid base pair because there's 1 hydrogen difference, and so is number 5. Don't forget number 5 is Shaq because we have NH3 and then we have NH4 plus. Notice that the difference in hydrogen is just 1 hydrogen difference. All right, question. Oh man, I just gave the answer. All right, so
I didn't see that. I didn't see it.
Yes, you did. Y'all all did. So acid in this equation is going to be HNO3 because it donates the hydrogen. If we look, we have HNO3 and then water accepts that hydrogen. So just like water, any polyatomic ion that has a hydrogen present can act as either an acid or a base. Just like water, it depends on if it's in the presence of a stronger or a weaker acid. So our answer is A. All right. So the conjugate acid, so H2PO4 minus is actually what the question has in it. H2PO4 is the incorrect formula, and PO4 3 minus is a base. So any polyatomic ion that's got a hydrogen in it, it can donate and accept a proton, right? It just depends on, is it in the presence, stupid pen, of a stronger acid or a base. So H2PO4 minus will act as an acid if it's in the presence of a what? Just like water. Think about water. Water acts as an acid if it's in the presence of a
Base.
base. And it would act as a base if it's in the presence of a
Acid.
acid. So it has to be a stronger or a weaker acid or base, right? Depending on what it is. And because water is essentially neutral, it can act as either one. It doesn't have to be a strong or a weak acid or base. All right, next question. Our answer to this question is D, because it has one less hydrogen. It is the conjugate base. If I was looking for the conjugate base for A, it would be H2PO4 minus. The conjugate base for B would be HPO4 2 minus. And C has an incorrect formula. All right, next question. So our answer is A. All right. And we got our acid, we got our two acids and our two bases. All right. And remember, the product side is always going to be the conjugate side. So if we're looking in the forward direction, the right side has the conjugates. If we're looking in the left direction, then if we're going in the reverse direction, the conjugates would be on the left side. All right, so we're gonna take a look at some strong and weak acids or bases. And here we go. So here's the chart. What do you need to memorize? These are strong acids. That's it. These. And these right here, those are our halogens, right? Our, what do we call it? Acid halides. So those are all strong except for, where's it at? HF, which is going to be.
Sorry. Auntie, you said you're making eggs. Do you want?
I want some eggs.
One. Hey, yo, Sharon, please. I'm hungry.
I was on.
So
Can I get a
acid
side of bacon?
Are going to be strong except for HF. So you don't really have to memorize the halides, right? Just know that HF is weak. And these are our two strong acids. We don't really look at perchloric acid, but for this class, that's up. You know what I mean? Those are the only two that you need to memorize. Everything else is going to be a weak acid for this class. And for our strong bases, anything with a hydroxide is going to be a strong base. All right, any compound with a hydroxide is going to be a strong base, and everything else are weak. All right, for the most part. So notice here the H2PO4 minus, that's a weak base. Notice that all of these, even HPO4 2 minus, right? That is also a weak base. It can act as either. So let's identify each of these as a strong or weak acid or base. We know that HBr, that's one of those acid halides, so it's going to be strong. HNO2, not HNO3. This is HNO2, so it's going to be weak. NaOH, it's got that hydroxide in it, so it's going to be strong. H2SO4, this is one of the ones that you just need to memorize. It's strong. And lastly, the OH, we've got lithium hydroxide, so it's also going to be strong. So let's take a look at writing the proton transfer reaction, which is just another way for saying, so if it's a halide, it's strong, except for HF, Akiyama. So proton transfer reaction is simply just the acid-base reaction between the phosphate ion and water. And we're going to determine in which direction the equilibrium is favored. So we start off with our phosphate ion plus water. And our products are going to be what? HPO4 2-, because we know that our phosphate is going to be acting as our base. And we're going to end up with hydroxide, right? Because water is going to donate the hydrogen to, it's going to donate the hydrogen to the phosphate. Now, looking at what we have here, we've got a weak base. Water is acting as a weak acid. HPO4 is also a weak acid, but it's a little bit stronger weak acid than water, right? Because remember, water really just wants to be neutral. And we know that OH is what? Is always strong. So remember, the direction of the acid-base reaction is always going to go from the stronger to the weaker. So which direction is our equilibrium favored in? I should have two arrows, but we're going to draw the second arrow. Which direction, what you call it? Are we going to go to the right? Remember, the reaction occurs from strongest to weakest. Is going to be the favored direction. So it's going to go, not right. It's going to go in reverse, because we're always going to go from strong to weak, not weak to strong. Remember, what does it mean to be a strong acid? A strong acid means that I want to give away my hydrogens. And once I give that hydrogen away, I don't want to take it back. If I'm a strong base, I want to eat up all the hydrogens. Give me all the hydrogens, like Cookie Monster. Give me all the cookies, right? And you don't give them back. Okay, Cookie Monster doesn't really eat them. He kind of just crumbles everything on the floor, but he's not giving them back, right? So strong base is going to grab all the hydrogens and not give them back. So we're going to go in the reverse direction, because that is the strong direction. Let's speed through these right quick. Let's speed through this one. Which of the following is not a strong acid? Yes, HF is not a strong acid. All of the rest of them are strong. These are those halides, right? So just memorize HF is weak and all the rest of them are strong. Ooh, this one is a little bit of thinking. You don't have it on your PowerPoint, but I want you to think about this one. Let's take a look at the answer. The answer is, wait, did I stop the question? I did not. Okay. The answer is C. And the reason why, let me see. The reason why is because for every 1 mole, where's my pen? I need a pen. No. For every 1 mole, I'm going to get 2 OH minuses, right? And so this should be an M. And this guy is only going to make 1 mole of OH in solution, because it's going to steal 1 hydrogen. So that guy is going to end up being CH3, CH2, 2, NH3 plus. And we're going to end up with OH minus in solution. And this is a kind of a weak acid. I mean, a weak, so it's going to be the lowest concentration. Whereas sodium hydroxide and barium hydroxide are both strong, but I'm only going to get 1 OH in solution for the NaOH. So that's why the answer is C. Did I write that right? Yeah, I did. All right. How much time we got? We got 2 more questions. So we are going to take a look at KBs and KAs and describe the acid base strength. So let's do this one together. The KB for the acetate ion is 5.6 times 10 to the minus 10. In this reaction, which are the strongest acid and base? So we have a weak base and a weak acid, and we have the stronger acid and the strong base. Remember, hydroxide is always going to be the strong base. So the answer is B. Okay? Did everybody understand that? Does everybody get that?
Oh, Professor, I have a
cool.
question.
Yes.
When I was looking at the orders of the question you posted for 7, it said like it was 7A.
Yeah, I
A,
know.
like the A. I thought it was like a
I'm
7B.
gonna fix the pictures later, but don't worry. It's the same questions. It's from the spring. That's why. Can I go over this again? All right. So when we're looking at this reaction, so the Kb, remember that's our dissociation constant for the acetate ion is 5.6 times 10 to the minus 10. And this is our acetate ion, right? So just looking at the Kb, what does this mean? Is this a strong or a weak acid? I mean, base, sorry. It's a weak base, right? So being that it's a weak base, that means this reaction wants to go in the reverse because it's not strong. And the reaction is going to produce hydroxide ions, and hydroxide is going to be the stronger base than the acetate. So that's why B is the answer. So why is it a weak base? Why is what a weak base? The acetate? Because the Kb is 5.6 times 10 to the minus 10. Right? So remember, what is the K? It's the equilibrium constant. Don't forget what equilibrium constants mean. However, it's a special equilibrium constant. It's a dissociation constant. So what does it mean to dissociate? It means that, so even though we have this, it's going to dissociate the water. So for bases, the dissociation constant, if it's a polyatomic ion, it's dissociating the water, right? Or we can call it an ionization constant because it's forming ionization. Yes, we are going back to the challenge question. That's why I wanted to just run through these right quick so we can get to the challenge question. So if the Kb was 10 to the minus 6, it's still going to be a weak base. So anything that's less than 1 is going to be weak. So acetic acid is stronger because water wants to be neutral. Yes, you could say that. Yes. All right, so water can act as either an acid or a base like many other polyatomic ions, right? If I have an acidic solution, I'm going to have more hydronium ion in solution or protons in solution and fewer hydroxides. If I'm a neutral solution, I have equal amounts of hydronium and hydroxide. And if I have a basic solution, I'm going to have more hydroxide than hydronium, right? So for every solution, remember the Kw, remember Kw is OH minus times H3O plus, gives me 10 to the minus 14, right? So if the hydronium ion concentration is greater than 10 to the minus 7, then it's going to be an acid. If the hydroxide ion concentration is greater than 10 to the minus 7, then it's going to be a base. So let's do this one together. In an acidic solution, how does the concentration of the hydronium compare to the concentration of OH? What do we get for our answer here? Yes, it's going to be B. In an acidic solution, we have more hydronium than hydroxide, okay? If I have more hydroxide, then it's basic. If they're equal, it's neutral. All right, challenge question. Here we go. Last go round. Which of the statements are true? Does aspirin act as an acid or a base in this reaction? It acts as a what? It's donating its hydrogen, so it's acting as an acid. The conjugate acid of water is H3O plus. Yep, that's true. A solution containing 2 moles of this stuff will contain 2 moles of hydronium ion. Is that true? No. Oh, sorry. Go back. Oh my goodness. I did not stop my screen share. That was by accident. Let's just share it this way right quick so we can finish. All right, mute. So a solution containing 2 moles would not, because why? Because it's weak. A weak acid is going to have less than 2 moles, right? And we know that it's a weak acid. Why? Because we've got the double arrow, and water acts as the base in this reaction. So the answer is D. All right, people. It is 11:02. We got all the way through the end. I want to say this. Make sure you watch the videos for Unit 9, Part 2, because we're going to go straight to the questions on Monday. All right, guys. See ya. Have a great weekend.